So welcome to Saturday morning chemistry. I have one physics principle I'm going to milk for all it's worth, but outside of that, this is really all about chemistry. And one quick slide about my current organization, International Council on Clean Transportation. No one ever heard of us before this. We're only about 10 years old. It's a relatively small organization, but the most important point is we do most of our work in other countries. We're a nonprofit research organization, and we primarily with government regulators worldwide. This is the only organization I know of that deals primarily with government regulators. And so in the US, EPA has maybe 400 people working on vehicles. When we first started working in China, they had maybe 1.5 doing the same thing. And so we almost become their staff, provide them information, data, advice, and our analyses and data had better be accurate or they're not going to listen to us. We deal with almost all aspects of transportation. We're funded primarily by foundations. We also get some money from research projects and contracts. We have offices in Washington, D.C., San Francisco, Berlin, and Beijing, although there's not actually anybody in the Beijing office yet, but that's coming. So I'm going to start off talking about something that I haven't ever prepared before, which is why are NOx emissions in diesels a problem? And then we'll just get into some background as to why we did this testing in the US on the diesels, talk about the testing itself, talk about the aftermath. So starting very basically, in the air, 21% oxygen, 78% nitrogen, and 1% whole bunch of other things that we can ignore. And so in an engine takes the oxygen from the air, combines it with the fuel. Fuel's there's a lot of different compounds, but they're all some variations of hydrogen and carbon. So you combine the two, and the hydrogen combines with the oxygen to form H2O, water vapor, and it combines with the carbon to form CO2. And then all that nitrogen just goes through and has no impact on anything. Unfortunately, that's not what actually happens in the real world. You get some unburned fuel coming through, primarily because of when you get close to the cylinder walls, crevices in the cylinder head, the temperature becomes too low to support combustion and it flames out and the fuel comes through unburned. Carbon monoxide is generally mostly partially oxidized fuel and when you don't have enough oxygen. And then nitrogen oxides, unfortunately, at high temperatures, they will react with oxygen and form nitric oxides. And this formation is proportional to the combustion temperature. A really, really important thing for what I'm going to talk about. So this is the one physics principle in my talk. So, and I have to change the cameras here. And so we're just going to do a simple demonstration of what we're talking about. So in an internal combustion engine, one of the 4 strokes of the engine is a compression stroke, in which they literally compress it. And what's really important to understand here, and I'm going to come back to this in the next slide, is that here's the piston. This is just the device to measure the temperature of what's in here, connected with the tube, and then here we have temperature gauge. And so as you compress the fluids, the temperatures rise. And you can see that on the thermometer. So I'm going to come back to that. But of course, the other thing that happens is that once combustion starts, you get another very large rise in temperatures, which you can see coming up here. Also, you see the piston coming back up due to the increased pressure. This doesn't actually happen in an internal combustion engine. It'll hold that flat, so the temperature rise is even faster. Okay, so much for physics. The other important principle here is the differences between gasoline and diesel engines. And it really starts from the presence of a throttle. A throttle is what just simply sits in the air path of into the engine and controls how much air enters the engine. Gasoline engine does this so that they can mix the air and fuel together, called homogeneous. It's pre-mixed, so you get a very thorough mixing of the fuel. You want to run close to the ideal air-fuel ratio, which is where you have exactly the right amount of oxygen to combust all the hydrocarbons. And I forgot to switch back, sorry. Thank you. Special apologies to people in the other room. But, and so, yeah, so you want to try to run close to the ideal air-fuel ratio, which is about 14.6 to 1. Now, because you're pre-mixed, you can't have the fuel igniting spontaneously. You got this compression stroke going on. Temperatures are rising, and the fuel can just ignite on its own. So to control this, you need very high octane. Octane is very simply just a measure of the fuel's resistance to being spontaneously combusted. And then you want to control the timing with a spark plug. Diesels don't have a throttle. They take in the full amount of air all the time. Therefore, they always run lean, sometimes at very, very lean air-fuel ratios. And because of this, the way you control the timing of the combustion is by when the fuel is injected. So just that compression stroke has raised the temperature enough so that the fuel when injected will immediately ignite. And now for that, of course, you want a fuel at very low octane. And diesels are only about 15 to 20. So the advantage of the diesel is that it takes energy to force air past the throttle when it's only partially open. That's a loss in efficiency of the engine. Diesels don't have that. Also, because diesels run so very, very lean, they have lower thermal losses in the engine. So there's two different ways in which they're inherently more efficient than a gasoline engine. Now, if you're looking at engine-out emissions, this here has simply the amount on the y-axis. The x-axis is the air-fuel ratio. So that black bar in the middle, that's the ideal stoichiometric ratio. To the left of that are rich mixtures. To the right of that are lean mixtures. And so hydrocarbons actually has approximately its lowest engine-out emissions, close to the stoichiometry. CO, on the right-hand side where it's lean, CO is very low. But if you start going rich to the left, it climbs very rapidly. Partially oxidation, not enough oxygen to support complete oxidation. NOx emissions are actually at their highest, close to stoichiometry and the air-fuel ratio. And something that's also important, and it's a common misconception when it comes to diesels. Now, when I was at EPA in the early 1990s, we did a test program where we actually measured emissions and other factors on a second-by-second basis. And one of the interesting things is that the Escort at that time had what they called lean-on cruise. So if you cruise down the road on the highway for a little while, it would actually switch and run lean for better efficiency. And so it gives me a chance to actually point out some actual test results. So the top line here is the air-fuel ratio. On the left-hand side, it's running at stoichiometry, and then it goes lean. And it's only about 18 to 1, which is not real lean by diesel standards, but it is by gasoline standards. And you can see the drop in the engine-out NOx emissions when this happens. So diesels, because they run usually more in the 40, 50, 60 to 1 air-fuel ratio, their engine-out NOx is actually an order of magnitude less than the engine-out NOx from a gasoline engine. This is very commonly misunderstood. I'm constantly reading reports about the high engine-out NOx from a diesel. No, engine-out NOx is very low. So what's the problem? Now we get into the catalyst efficiency, and this is a gasoline system, a typical three-way catalyst. Again, we have air-fuel ratio on the x-axis. The y-axis is now percent efficiency. And you have the window in the middle near stoichiometry. What you're seeing here is that on the left-hand side, for CO and hydrocarbons, when you go rich, the conversion efficiency drops very, very rapidly. That's because you need excess oxygen to oxidize HCl. NOx is completely different. NOx, you're trying to separate nitrogen and the oxygen. And so you're creating oxygen in the reaction. If there's already excess oxygen around, that reaction will not happen. And you can see that here, where the NOx reduction drops off very, very rapidly when you start going lean to the right. There's a narrow window in which all three reactions will happen simultaneously. And the key to this, as manufacturers have found over the last 20 years, is incredibly precise air-fuel control. If you can keep your air-fuel ratio dead on stoichiometry, you can simultaneously have all three reactions happen at more than 99% efficiency. So that's 2 orders of magnitude. And again, go back to this test program and just try to illustrate what's going on here. On the left-hand side was an early 1990s Grand Prix. The air-fuel ratio is at the bottom in the black bar. It's oscillating around 14.6. The dotted line is the NOx efficiency, and that's on the left scale going up to 100%. And you can see that every tiny little lean excursion, in other words, whenever the air-fuel ratio goes to more than 14.6, there's an immediate and large reduction in the NOx efficiency. The vehicle on the right, the Grand Am, has a little better air-fuel control, but it also biased it slightly rich so that it never went leaner than 14.6, and the NOx efficiency stayed at virtually 100% all the time. And modern gasoline engines, they're all doing this now. And we go back to our lean on cruise Escort. Same thing happened. The air-fuel ratio is the black line. The first part, it's at stoichiometry, then it goes lean, and you immediately see this drop. You see the conversion from almost 100% NOx efficiency to 0. So three-way catalysts don't work on a diesel engine. It always runs lean. And therefore, the tailpipe NOx is an order of magnitude higher because you lose this 99% efficiency, even though engine out emissions are only 10% of what they are in gasolines. So in order to pass standards, they need solutions that work in a lean air-fuel ratio. I'm going to do it, not too good. And there's 2 different solutions that have been developed. One is called a lean NOx trap. And that's the can kind of right in the middle of this picture. And it's literally what its name describes. The device traps the NOx as it's coming out of the engine. Now, of course, it fills up. And so to regenerate the trap, every 30 to 60 seconds, the engine has to be forced rich. And the excess fuel will take the NOx off of this trap and will reduce it. Okay? It works reasonably well. There are some downsides. One is you're injecting extra fuel. There's about a 4 to 5% fuel economy penalty involved with the system to regenerate the trap. Another problem is that at higher loads, if you're accelerating faster or going at higher speeds, the trap tends to be overwhelmed and doesn't work as well. So it's most efficient at very low loads. Remember that too. The other system is called selective catalytic reduction. And what this system does is that it injects urea into the exhaust, and that urea serves as the agent to reduce the NOx. This system works better. It can handle higher loads better. It is more durable, but it's also a lot more complicated. Urea is just a way to inject ammonia into the engine, and I'm actually doing this out of sequence. Okay, first of all, you need a tank for the urea. That's called the AdBlue tank here. AdBlue is Mercedes' brand name for urea. So you have to have a tank, you have to have a refill tube, you have to refill it periodically, you have to have a line to take it to the exhaust system, you have to have a fuel injector right in the exhaust to control the amount that's being injected. And that's because if you don't inject them enough, you don't get the reduction in NOx. If you inject too much, you get ammonia coming out the tailpipe, which is not really desirable. And then the other issue is that EPA requires that the system be monitored to make sure that it actually has urea in the tank. It's not empty, hasn't been refilled with something else. And it also requires that the manufacturers have some sort of way of alerting the driver that they better do this, such as eventually either not allowing the engine to be restarted or reducing the power of the engine. And the final thing is that urea freezes, so it has to be heated and insulated. So a lot of additional complexity, a lot of additional cost. You don't have a trade-off with fuel economy anymore, but you do have a customer issue with having to refill the urea tank. And so some customers really don't like this. So cost. We did a study 3 years ago looking at the cost of after-treatment systems. And so these are the European regulations that we have listed on here. And the reason I've chosen those is because the step from Euro 4 to Euro 5, they primarily made the particulate matter standards a lot more stringent. And that required particulate traps. And then from Euro 5 to Euro 6, they finally reduced the NOx standards and forced NOx after treatment on the diesels. But you can see the gasoline line, this kind of greenish blue line, meeting these more stringent standards for gasoline engines is easy and cheap. 99% catalyst efficiency. You just got to make sure you got good air fuel control. Diesels, adding the particulate trap from Euro 4 to Euro 5 added about $450. And going from Euro 5 to Euro 6, adding a lean, and this is actually an estimate for a lean NOx trap, another $450. So $450, manufacturer cost, not what they're going to actually put on the vehicle. And the selective catalytic reduction systems are even more expensive, probably about $550. And then they scale with the size of the engine. This is for a 2-liter, which I selected because it matches what VW used in their feed devices. Okay, now let's talk about emission standards and what led us to set up our program in the first place. So this is history of emission standards in the US and Europe, and the X scale runs from 1996 to 2028. Europe, there's 2 different lines. One is the gold line, the other is the green line. And that's because Europe traditionally has had different emission standards for gasoline and diesel vehicles. One of the ways in which Europe has subsidized diesels is to hold them to less stringent standards than gasoline vehicles. So the gold is the diesel standards, and the green is the gasoline standards. And you see that finally for Euro 6, they're starting to converge, and they are supposed to converge completely in another 3 or 4 years. The US, you have the federal Tier 2 standards, which are the kind of the red line, and then the California Lev 2 standards, which are the blue line. Those are also converging now, but they are more stringent and have been in the past, will continue to be in the future. The US standards are more stringent than they are in Europe. And I'm specifically showing the difference between the diesel and the gasoline standards in Europe. So back for Euro 3, the diesel's NOx standards, this is just for NOx now, the diesel standards were 3 times what they were for gasoline. That continued through Euro 4 and Euro 5. Finally, in Euro 6, they've reduced that gap. There's still a 33% gap, but at least it's not times 3 anymore. Now, when you measure vehicle emissions for compliance, this is all done under laboratory conditions. That's essential because the tests have to be repeatable. If you don't have a repeatable test, the manufacturer doesn't know what they have to do to comply. And so every country that has standards, and throughout the history of having standards, they've all done this. So you take the vehicle into a laboratory, you strap the vehicle on a dynamometer, and you drive it. And you also have preset test cycles, specific traces of speed versus time. And you can't quite see it here. The number 2 on the picture to the left, there's actually a screen there that's mounted on the driver window. So the driver's staring at the screen. It shows them the trace they're supposed to hit, shows them what he's actually doing. He's got to try to match the 2. It's kind of like a video game. So here's another point here. The top left, this is called the NEDC. This is the test cycle that's used in Europe. It's kind of hard to see because it's compacted to 600 seconds and just maybe an inch and a half on my screen. But it has a lot of plateaus on speed. This cycle has a lot of cruise conditions, has a lot of idle time. It's a very low cycle. Remember I was talking about lean NOx traps and SCR systems? Lean NOx traps work on this cycle. It's low load. Europe is in the process of changing their test cycle. Starting in 2017, they're going to introduce the WLTC, the Worldwide Harmonized Light-Duty Test Cycle. It will help things. It has higher accelerations, a lot more transient driving, not nearly as much cruising. And in fact, if you compare that cycle on the upper right to the US cycle on the lower left, they're actually fairly similar. If you do calculations of acceleration and loads and so on, they work out to be pretty much the same. So that cycle should help once it's finally adopted in Europe. And the US also has some other supplemental cycles to deal with specific conditions like air conditioning operation. On the US 06, if you can see it in the middle on the bottom, it's a very, very aggressive cycle, very high accelerations, very high speeds. Now, the test cycle makes a big difference. And this is testing that was done in Europe on Euro 6 vehicles. And the lighter blue bars are with the selective catalytic reduction system. The dark blue bars are with the lean NOx traps. So way over on the left is the NEDC. That's the current official test cycle used in Europe. And those are the emissions that were emitted by these vehicles on that test cycle. Every other test cycle they ran, I'm not going to go through the description, every other test cycle they ran generated much higher emissions. And in most cases, with these higher loads on these other cycles, the selective catalytic reduction systems did better than the lean NOx traps. So this is my summary slide for historical emissions. And so I've got 4 clouds here, starting with Euro 3 on the upper left, going to Euro 6 on the lower right. The dotted red line is the standards. This is what the standards are allowed to emit under the official test cycle. And everybody's meeting that. The gray cloud is assessments using portable emission measurement systems in the real world, assessments of the emissions that are actually happening in the real world. And you can see that from Euro 3 to Euro 6, the end-use cloud has come down, but it hasn't come down nearly as much as the standards have. So standards have come down 85%, and use emissions have only come down 40%. So this is a well-known problem in Europe. They don't know the causes of it, but they know that's a problem. And it's confirmed by remote sensing data. This is where you take some sort of a laser gun or something and just point it at vehicles passing by, and you get a snapshot, instant snapshot of what their emissions are at that particular point. It's not very precise, but it's great for trends. And so here we're looking at the trends. On the left side is gasoline. The solid line is the standards. And you see how the standards in Europe have been coming down over time. And then the blue diamonds are the average of all these remote sensing measurements. And, there's tens, hundreds of thousands. And they track pretty well. As the standards come down, the gasoline emissions have also come down. Right-hand side, same thing for diesels. Solid red line is the standards. And then you have the remote sensing data, which seems to have no correlation to the standards. So this is the background. This is the background for what we did. We had this bright idea that, okay, we know that there's a problem with emissions in diesel emissions in Europe, and so let's come to the US. And because EPA and CARB have more stringent standards, but more importantly, because they have much stronger legal authority and much more expertise in enforcement, we expected the diesels to be clean in the US. And then we would test these vehicles in the US and take them back to Europe and say, hey, they're clean in the US, how come you guys can't do it in Europe? And to illustrate, well, I actually try to remember to talk about that later. So the California Resources Board provided laboratory testing for these vehicles. We definitely wanted to know what the baseline was for these specific vehicles in the lab. And a couple more pictures here. The upper left is showing the roller that the vehicle is strapped to. This is dynamometer. And so It's actually used to control the load as the vehicle is being driven. The lower left is shooting up underneath the vehicle, looking at part of the after-treatment system. What I really want to point out here is on the right-hand side. I want you to take a look at these boxes. These are the analytical equipment that is used in the official test. And here's what they have to be when you do a portable emission measurement system. So you got to take those boxes, you got to shrink them down and make them really small. And so to do this testing, we contracted with West Virginia University because they had one of these units. These are highly specialized, very expensive units. And so we contracted them to actually do the testing with us. The analytical equipment are those two boxes on the left-hand side, the red and gray box on the right. That's the battery pack. These things take a lot of juice, and you can't be drawing that off the engine because that changes the emissions out of the engine. So we have to provide our own battery pack for that too. And the other thing is that all this measurement equipment only measures concentrations. What's the percentage of NOx in the exhaust? And so to actually know the mass flow, the amount of grams, you have to measure the exhaust mass flow. And so if you look more towards the bottom, on the left-hand side, you have those two red wrapped pipes. That's where you go in, you collect the exhaust, you bring it up, run it across, so that these emission measurement systems can sample the exhaust and know what the mass flow is as well. The testing plan. We wound up selecting 3 vehicles. We picked the VW Jetta because it's the largest selling diesel in the US. Diesel sales in the US are less than 1% of the market, but still, it's the largest selling one in the US. We picked the Passat because the Jetta used the lean NOx trap, and the Passat uses selective catalytic reduction. And we wanted one of each from a modestly priced vehicle. And then the third vehicle, we wanted to be a more expensive Highline diesel. We got into a little trouble over this. If you go read the report, it says that we were going to test a Mercedes diesel. The head of our European office used to work for Mercedes. And so there were reports appearing in the press saying that Mercedes had called him up and pressured him not to test one of their cars. The reality is that we could not find a single Mercedes diesel for rent in the entire state of California. And so we switched to a BMW X5. The testing routes. We did 5 different routes that we tested these vehicles under. Route number 1 is simply a highway route. Drove from Los Angeles to Ontario, California. Route number 2 is interesting. The original, the FTP cycle, the test cycle itself, it was developed in the late 1960s. California Air Resources Board had picked out a driving route in downtown LA. EPA sent out 1 car and 6 drivers, and so these 6 drivers drove this car over this predefined route, and they used state-of-the-art measuring equipment, which was a strip chart recorder, late 60s. And then when they were done, they took these 6 strip charts, put them up on a wall, picked out the one that was in the middle, voila, FTP. And so what we did here is we went back and we tried to recreate that route as closely as we could. We also selected urban routes in San Diego and San Francisco, and then just to see what would happen under really high load conditions, we drove the vehicles up into the mountains and back. That's route number 3. We also took 1 vehicle and drove it from Seattle to San Diego. I'm not going to talk about those results because we only had that on 1 vehicle. So here's the test results. So we have 3 vehicles, which in our report we called vehicles A, B, and C. And on the y-axis is not emissions, but emissions as a multiplier of the standard. So for example, where it says 10, that means 10 times the standard. And so, and then we have 5 or 6 bars for each one of these vehicles. There's actually a couple of tests that we missed doing. And they go in the same order, route 1, the highway, then the LA, then route 3 going into the mountains and back, and then the other 2 urbans. And then the 6th one is the FTP, which if you look really, really hard, you can see 2 tiny little red bars. These vehicles passed the standards. when tested in the emission laboratory. And we got out in the real world. West Virginia University has talked to reporters too, and they've talked about how when they first started getting test results, they thought there was something wrong with their equipment. They kept recalibrating. And said, no, still getting the same result. When I first saw the results, I thought there was something wrong with the vehicle, a malfunction, that it literally wasn't operating properly. But then we realized that, no, it was tested at California Resources Board and passed the standards. It's got to be operating properly. And so we basically wound up collecting this data and trying to decide what to do with it. You know, I had a lot of experience in the auto industry. I was reasonably sure these things had a defeat device on them, but the words defeat device are not something you ever say unless you're absolutely sure, especially when you're talking to a company that has the ability to sue us into oblivion. And so we actually put out the report itself. We labeled them A, B, and C. We did not identify them. We even debated whether we should make the report public. We did finally put it on our website, but we had no announcements that we had put it up. We sent the reports to CARB and EPA, said we think we should take a look at this. We sent a courtesy copy to VW in which you said vehicles A and B are yours. And I'll get into the timeline later. But you can see these emissions are incredibly high. The Passat with the selective catalytic reduction, it ran 5 to 18 times the standard, and the Jetta ran 15 to 35 times the standard, and this was all the time. This is not isolated events. This is not high load operation. This is all the time. Now the VW X5, we got our example. Except when we ran it into the mountains and back, it was at least close to the standards under all these different driving cycles. So yes, diesels can be clean. This is the same graph, same order of emissions, going from the urban LA and so on, but I've added one more bar on this graph. In 2012, West Virginia University took a 2011 Mack truck and drove it coast to coast. This vehicle, 18-wheeler, they loaded it to 67,000 pounds, 33.5 tons. And I pulled out the one day they drove through the Rocky Mountains, and the average of the other 5 days they drove was 0.39 grams per mile. The Passat NOx emissions on the highway, that's the brown bar, on the highway, so it's same conditions, running down the highway, was 40% higher than this Mack truck. And the Jetta was 2.5 times the Mack truck. So, I mean, this is not some small matter. And even in the US, in which diesels are 1% of the market, and in use are even less than that, someone has already done an assessment and said that just this excess emissions from these vehicles might contribute to 300 or 400 premature deaths each year in the US. Now you go to Europe, 53% of the market for diesels. So this whole thing is a much, much bigger deal in Europe than it is in the US. And then the final slide is these 3 tests were then combined with 12 tests that had been done in Europe in what we call the meta study that we put out in October 2014. And so once again, we didn't identify what the vehicles were. Vehicles B, F, and H are the 3 US tests. B's down on the bottom on the right. F and H were the 2 VWs. And you can see that the VWs are high, but they're not out of bounds with what we've seen in some other vehicles in Europe. Okay. Timeline. We contracted with West Virginia University in February 2013. We finished up the testing and the report in May 2014, sent it to CARB and EPA, as I've already described, and they launched their own internal investigations. In December of 2014, VW conducted a voluntary recall. And this is the thing that I find the single most perplexing and hard to believe part of this entire thing. VW went out there and recalibrated their vehicles and swore up and down the carbon EPA that this would fix the problem. They didn't take the defeat device out. 5 months later, May 2015, CARB went out and got some of the vehicles that had the fix in them, tested them, emissions were still high, hauled VW back in. It's like, you know, what the heck's going on here? VW had a chance to fix this. They could have had a recall, told the agencies, hey, we got to change some hardware, and of course, whenever you change the hardware, we have to reflash the computer memory, quietly take the defeat device out at that time. None of this would have ever happened. Yeah, they had a recall, made a little publicity, probably some fines. They never would have had to admit they had a defeat device. This scandal would have never happened. But I do not understand, so I do not understand how VW could have been so colossally stupid. It's just, so in August 2015, EPA and CARB finally told VWs that we're not going to let you sell any 2016 diesels until this is resolved. So September 3rd, VW finally admitted there was a defeat device. September 18th, EPA and CARB issued the notice of violation, and for the next 2 months, my world as I knew it ended. And let's see if I can get this going.
Locked away in VW's headquarters, a car plant the size of Gibraltar, bosses have been meeting today to decide the company.
Now to new allegations against Volkswagen, which the U.S. government says.
Volkswagen の排ガス不正問題をめぐり、不正を見抜いたカリフォルニア州当局の担当者が。
Es hat etwas von David gegen Goliath oder besser gesagt von Dre und John.
They're Volkswagen's highest-end brands now. They too have been dragged into the company's emissions scandal.
Faktisk så afslørede ICCT allerede i denne her rapport for et år siden, at
Our company was dishonest with the EPA.
Drew Kojak is the executive director of the International Council on Clean Transportation, the group that helped to tip off the EPA. I've read the documents and I've read the story.
From WBUR Boston and NPR, I'm Tom Ashbrook, and this is On Point, a massive scandal at Volkswagen.
Franco, que dirigió la investigación de la ICCT, por sus siglas en inglés es la International Council of Clean Transportation, es la que ha desenmascarado el engaño de los sistemas de emisión de gases contaminantes en los vehículos diésel de Volkswagen en Estados Unidos. Señor Vicente Franco, ¿cómo está? Buenos días.
Hola, buenos días. ¿Qué tal?
¿Cuánto tiempo les ha llevado a hacer esta investigación?
Drew Kojak, it was your organization that sponsored the test, ironically, because you thought you'd be proving the reverse.
That's exactly right. We did this study not only with West Virginia University, but also with the help of the California Air Resources Board.
A esta hora es un placer saludar al ingeniero Francisco Posada. Es colombiano y nos atiende a esta hora en la W. Ingeniero Posada, buenos días.
Buenos días y muchas gracias por la invitación.
Francisco tiene un grado en Ingeniería Mecánica en la Universidad del Valle en Colombia.
John German of the International Council on Clean Transportation, which helped uncover the VW scam, says those OBD tests won't identify VW cars that haven't been fixed.
No, those programs will not pick up that the fix was not done. Now, the state has the ability to compile a list of recalls and to check to see if this vehicle has had the recall.
California is one of the few states that has such a program. It's linked to the state's vehicle registration system.
We do know that the vehicles have had defeat devices on them since 2009, so that's certainly some years. We also know that we've gone down this road before. That heavy-duty manufacturers used defeat devices in the United States way back in the late 1990s. And so this is an issue which we've encountered before, and I think I was surprised, I think my group was surprised when we encountered it, or we heard about it again, that Volkswagen was doing it now with their light-duty passenger.
The funny thing about this scandal is that it starts in the US. But the actual problem with diesel NOx emissions is not a US one, it's an eminently European problem.
Faktisk så afslørede ICCT allerede i denne her rapport for et år siden, at nye europæiske dieselbiler i gennemsnit udleder 7 gange mere NOx end EU's grænseværdi.
Those are really scary numbers on that. Yeah, that's pretty bad, yeah. That's the dimension of the problem that we're facing.
Clearly, the agencies have to be vigilant, and that applies to every country. It's not just Europe, it's China, India. You need agencies who can be vigilant and can monitor and enforce requirements if manufacturers are found not to be compliant.
Okay, so how do I? All right. I guess I just stopped it. So I also, you know, there's a few of my favorite political cartoons. I mean, one of the problems with this is that these vehicles got better fuel economy in the real world because of this. And so VW did sell it as a feature. And just to help illustrate that while the publicity in the US has died down tremendously, I don't get many calls anymore, the same is not true in Europe. This came out last month in Stern magazine in Germany. I don't even know what it says. But they like my garage. And I just got done rebuilding the engine in my vehicle, and as usual, I haven't cleaned anything up. So they thought that was great. Don't ask me why. So anyways, let's finish up the timeline in the U.S. In November, the first notice of violations were all for VW's 2-liter diesel engine. And it was both for the lean NOx trap using the Jetta and for the selective catalytic reduction system using the Passat. But in November, they issued another notice for VW's 3-liter engines. And this now includes Audi and Porsche products as well. VW initially denied it had a feed device. It's actually quite interesting. And later, and what they're saying now is basically that the calibration is a defeat device in the US, but it's not a defeat device in Europe. In January, US Department of Justice issued a civil lawsuit. And if you go read that, one of the interesting things they talk about is their complaint that VW will not turn over any information on individuals, citing privacy laws in Germany. So the Department of Justice is not happy about that. And VW is supposed to meet with CARB a few days ago about their recall plans for the 3-liter. Haven't heard any results yet. The meeting for the 2-liter has already occurred, and CARB and EPA have rejected VW's plans for fixing the problem. So the saga is still very much ongoing. In Europe, just a few days after the notice of violation in the US, VW admitted that they had 11 million diesel cars worldwide with defeat device software. I'm just going to pick a couple of these out. October 28, 2015. I have a slide a little later talking about real driving emissions. Europe was actually already working on a new provision that would require this PEMS testing in the real world. It would only be on certification vehicles, not on real-world vehicles, but still a step in the right direction. And part of this is to set what's the levels that you have to meet under these real-world conditions to pass. And on October 28th, this technical committee met and relaxed the standards for this requirement. So a month and a half after the scandal broke, they were relaxing requirements on diesels. And what I heard, so don't quote me on this, so it's being recorded, is that there was concerns that the scandal was costing VW a lot of money and they didn't want to impose another expensive provision on them. November 26, VW announces a flow transformer for the 1.6-liter engine to fix it. This is a $10 piece of plastic that they say is going to magically cause everything to work better. January 14th, the European Investment Bank stops making loans to VW. The other thing I want to focus on, and I'll talk a little more about later, is January 27th. The European Commission has actually come up with a very constructive proposal. Another interesting thing is on January 14th, the French government conducted a raid on Peugeot offices. Nobody's talking about why they did it. Everybody assumes it's connected with the scandal. We know that they've been doing a lot of testing and investigation in France, but it's only conjecture as to what it was. January 19th, Renault voluntarily recalled some of their vehicles to fix calibration issues, but made very clear that they were doing this voluntarily, not because they had a defeat device. Switzerland has banned sales of VW cars. There's a number of investigations going on. Interestingly, okay, this is only 2.5 months, but still, in those 2.5 months, diesel sales in Europe couldn't have fallen off a huge amount because the overall sales for the year are only down by 1.9%. South Korea. There are 2 other countries outside of Europe that have a lot of diesel passenger cars. Those are India and South Korea. And so South Korea, they very quickly started an investigation on November 26th. They ordered a recall and a fine. January 21st, VW's recall plan was rejected, and they have filed criminal charges. There's also been voluntary recalls by VW in India and China. In Brazil, they've not only recalled but paid a small fine. And Chile has asked VW to stop sales of the VW vehicles. Okay, now I'm going to do my own little Q&A. Because there's 3 questions I always get asked. Why did they cheat? To help put this into context, VW was on a campaign to become the #1 sales leader in the world. And the US part of that goal was to increase their sales to 800,000 vehicles a year from 300,000, almost triple sales. So tremendous pressure on everybody to try to control costs. And as I showed before, these after-treatment systems are very expensive. And so by fudging on this, VW might have been able to install a less expensive system. And in fact, considering the difficulty VW is having getting approval for their recall plan, I think that's a pretty safe bet that they put in a system that is not adequate and save some money on it. I've already talked about the trade-off between fuel consumption and NOx emissions for lean NOx traps, because you have to inject fuel to regenerate the trap. Select catalytic reductions. It's the urea refill interval. Most customers are okay if they can have this done at the same time that they have the oil changed. But if you start having to refill more frequently, it can lead to complaints. And these are all possible reasons. I don't have any real data on why VW did it. The last one, though, which is not as well known, is there's also a trade-off between fuel consumption and NOx emissions in the diesel engine itself. And I have a graph here. This is from a 2002 report by Volkswagen. And here, what we're looking at on the x-axis is the timing of the fuel injection. I talked earlier about how the fuel ignites almost immediately after it's injected. So if you control injection, then we have the top red line, that's fuel consumption. So as you delay injection, fuel consumption increases. The black line is soot or particulate matter. That dramatically drops. And then the red squares with the blue line, those are the NOx. That also dramatically drops. So that you can get a lot of control of engine out NOx by retarding the fuel injection timing, but your fuel consumption goes up. So here's another trade-off. And we have an upcoming report coming out that suggests that this trade-off might be in the order of 4 to 5% as well, on top of the 4 to 5% for the lean NOx trap trade-off. So, these are, again, it's conjecture to a large degree, but some of the possible reasons why they did it. How do you do it? Well, official test, you take the car, you strap it on a dynamometer. The non-drive wheels don't turn. Every car has analog brake system. They measure they're constantly monitoring the rotation of every wheel. So that's one easy way. The steering rack doesn't move. You know, you're not turning on the dynamometer. The official tests are always run between 70 and 80 degrees Fahrenheit. Renault has admitted that they change calibrations at higher and lower temperatures in Europe. The engine itself is soaked so that the engine at the start of the test is cold. You might not think 70, 80 degrees is cold, but the normal operating temperature is 200 degrees. And so they start with a cold engine at that same temperature. And BMW in Europe has said that if the engine is restarted when it's hot, they change calibrations. And then the last one, there are others, but these are the main ones, is I talked earlier about that speed versus time trace. The whole speed schedule is prescribed. And there was a hacker in Germany who happened to own a VW diesel and decided to hack into the software on his own car. And he made a presentation at some giant hacker convention a month ago about what he found. And you can go find this on YouTube. And if you do look it up, you start about minute 48. And what he found is that he found software that was tracking the distance versus time, which is just another way of expressing speed versus time. And that there was this window, if the distance versus time stayed in this window, they would keep the emission control equipment turned on, but if it fell outside that window, they'd shut it off. This is for the VWs. And the third question is, how high did this go within VW? You know, I spent 20 years working for automobile manufacturers. Engineers like to do a good job. Part of doing a good job is not cheating. Certainly, you want to take advantage of every legal thing you can. If you're not doing your job. In fact, my first job at Chrysler, part of my job was finding every flexibility and loophole I could find in the fuel economy regulations and putting this into where, this is late 70s, early 80s, oil crisis. It was a big deal. Then when I moved to EPA, the first thing I did is to close those loopholes. But I knew what they were. And so engineers on their own are not going to do this, but it could have been, originally when I was talking about this, I said, it could have been a fairly low-level manager who just said, hey, we've got these targets we've got to meet, I don't care how you do it. But the 2-liter Jetta brought out in 2009 in the US had a lean NOx trap on it. VW added the diesel to the Passat in 2012. It used a selective catalytic reduction system. If you remember the diagrams, they're completely different systems. The software for the lean NOx trap is not going to work on a selective catalytic reduction. So in 2012, VW had to redesign that software for a different vehicle with a different after-treatment system. The 3-liter is designed by Audi. It's not even designed by VW. So how high did this go? All right, how am I doing? I got to wrap up quick. Now what? The primary focus for ICCT is not just defeat devices. Yeah, this is important, but there's a bigger concern in countries outside the US, and that's just in how compliance and enforcement is done in general. And so that's our current focus. We want to try to improve this in general around the world. And let's see, I'm just going to skip this and go on. Europe has a structural problem. The standards are set by the Environmental Commission for the entire region. Enforcement is done at the country level. And in fact, every country has agreed that they will accept compliance demonstrations in any other country. So what this leads to is manufacturers go shopping. Which country will do the least enforcement? And basically, enforcement in Europe is almost non-existent. There's never been a mandatory recall for emissions in Europe. And if you look at the kind of testing that's been done, I'm missing there we go. The blue boxes, the top is Europe, the bottom is the US. The blue boxes are testing done by the manufacturers, and the red boxes are testing done by the government. Conspicuously absent is any testing done by the government in Europe. The biggest problem in Europe is not defeat devices. It's in-use surveillance testing. That the You know, we talked about how VW is having trouble finding a solution in the US, but in Europe they're just going to reflash the software. Well, reflash the software means they're going to turn on the emission control equipment all the time, and the experience in the US suggests that emission control equipment is not going to be durable. But nobody tests vehicles in the real world over time in Europe, so it doesn't matter if the catalyst system deteriorates and goes away, because nobody tests. The US has very, very robust end-use testing requirements up to about 80,000 miles. And manufacturers have to pass emissions at 80,000 miles on real-world vehicles. Europe is doing real driving emissions, where they're literally taking prototype test vehicles and taking them out in the real world, putting PEMS equipment in them and measuring emissions. This is definitely a big step in the right direction. Right now, they're allowing these vehicles to have twice the emissions that they do on the official tests, and they are set up so that all of the more aggressive driving is excluded from the calculation. So it's not ideal. It could be a lot better, but it's still a good first step. And ICCT is already working to try to look at the next phase and extend this to in-use vehicles. If you have a certification vehicle, there's actually nothing illegal about manufacturers changing calibrations in the real world. For the vehicles, for the vehicles they actually produce from the pre-production certification vehicle. And so they could theoretically reinstall a defeat device after they receive their certificate. So we do think in-use testing on this is important, but definitely a big step in the right direction. And the other really nice things happened on January 27th, the European Commission put forth a proposal to overhaul their whole system and to try to have stronger authority over all of the countries and unify it. And then the other, did I put it on here? Yeah, I didn't put it on here. One of the things they're proposing that I think would be most effective is to allow individual countries to recall vehicles in their own country. Currently, that's not allowed. Only the agency that certified them originally can issue a recall. So that would be a real strengthening. Now, is this ever going to get passed? And that's really uncertain, but it's definitely at least a strong first step. So some implications. I'm actually, certainly the current test cycles are inadequate. We need higher loads, better test procedures. And I do tend to defend EPA a lot. People have criticized them for not finding this, but diesel cars in the US are less than 1% of the market. They weren't exactly focused on them. And look at what they've done once they found out. So EPA and CARB have all the authority they need. They have all the systems they need. They've already put out a letter saying that they're going to do oversight on diesel engines. In fact, they held up the certificates for every diesel in the US until they put them through an in-use testing program. And so, yeah, I'm not at all concerned about the US system, even though it's largely based upon laboratory testing. But Europe has a ways to go, and that's where our focus is right now. And then I just have a slide for background additional reading, which you can come up with. You can view on YouTube if you want when we're done. And I think I'm done.